Let's take a look at how vector quantities affect energy and work. Well, energy is a scalar. If something has a certain amount of kinetic energy, it doesn't matter what direction it's moving. We're squaring the magnitude of the velocity. There's no direction associated with this. If an object is moving to the left with some velocity, it has a certain amount of kinetic energy. At some later time, maybe it bounces off of a wall, it bounces back to the right, and if it moves with the same velocity to the right, then it's going to have the same kinetic energy. Work is also a scalar quantity, but vectors do affect the work done. Let's think about what happens when our force is in the direction our object is moving. So I have a cart that moves on low friction wheels, and if I push on it, I exert a force to the right, and if my cart moves to the right, then what's happening to the cart's speed, what's happening to its kinetic energy, and what can we say about the work I'm doing on the cart? The work I'm doing on the cart is going to be positive. It's going to be equal to the force times the displacement. I'll just use the magnitude of the force times the magnitude of the displacement. The cart's speed increases and its kinetic energy increases. But if the cart was moving in the other direction and I was pushing on it like this, then what would we say about the speed of the cart, the kinetic energy, and the work done? The cart is moving to the left, but our force is pushing it to the right, causing the cart to slow down as it continues to move to the left. In this case, the work done on the cart is negative. The speed of the cart decreases and its kinetic energy decreases. The way we account for the relative direction between the force and the displacement to calculate the work done is by using a dot product. Work is a scalar, and it's the vector dot product of force and displacement. Remember, the dot product returns a scalar quantity. Work is a scalar. We take two vectors, we take a dot product, we get a scalar back. And this is the same as the magnitude of the force multiplied by the magnitude of the displacement multiplied by the cosine of the angle you get when you put their tails together. So if the displacement is in this direction and the force is in this direction, the angle we get when we put their tails together is 180 degrees. And that's why we would get negative work done in this situation. So let's see if you understand this equation. Let's look at this example. Instead of pushing to the right on the cart, you're going to use a rope and pull at an angle of 30 degrees. And you're going to keep a constant force of 100 newtons at that constant angle, 30 degrees, the whole time you're pulling on the cart as it moves 5 meters across the track. What's the work done by your pulling force on the cart? So we want the magnitude of the force, that's 100 newtons. We want the magnitude of the displacement, that's 5 meters. And we want the cosine of the angle we get when we put their tails together. The displacement is to the right, the pulling force is at a 30-degree angle. So theta equals 30 degrees in this case. The angle we get when we put the force and the displacement, when we put their tails together, the angle that we get. (433 Newton meters, which is a joule. 433 joules. One more example. The cart is moving to the right, and you're going to pull back to the left with a force that's angled at 30 degrees with respect to the horizontal. What's the work done by that pulling force on the cart? The magnitude of the force, 100 newtons. The magnitude of the displacement, 5 meters. And the cosine of 150 degrees. The angle you get when you put the displacement and the force tail to tail. And in this case, we get negative 433 joules. Negative because we are slowing the cart down. We are reducing its kinetic energy, so we are doing negative work on the cart.